Hi, my name is Kolby ML, and this is Nick. We both work at the Ethereum Foundation, researching and implementing execution and consensus layer light clients. So let's enter the portal network. So Ethereum's kind of broken, and I know that's kind of like shilly, but it's more of a problem of how we access Ethereum. Starting out, Ethereum was very accessible. You could boot up a full node in maybe like 10 minutes and it would sync the full chain. But now, it takes days to sync the chain. And what? Oh, I'll just continue. Oh, crazy, okay. Anyways, as you see, it's a little blob. So it takes days to sync the chain, and because of that, most people access Ethereum through centralized providers such as Infura and Alchemy. This is kind of like crazy because I guess centralized sources was supposed to be the thing we're moving away from. Ethereum was supposed to be this accessible thing where you just ran this program on your computer and you were able to send money, but that's not really how people interact with Ethereum anymore. So I guess, how do people interact with Ethereum decentralizedly right now? And that's through full nodes. As you see on this image on the screen right now, to run a full node, you need around like 1 terabyte of storage, and that's really not accessible. And that's also not including the knowledge required to run a full node. It's like, if we want Ethereum to be used, you would want your grandma to use it. And that implies that you don't even need to know what a full node is in the first place. So it's like, what are we doing? So earlier I said to participate in Ethereum's core protocol, you needed to store around 1 terabyte of data. What if we took that terabyte and divided it into 1,000 pieces and put it on 1,000 nodes, but you could still look it all up on our network? And so if everybody only needs to store 1 gigabyte or so of data to access all of Ethereum, this lowers the requirement so you could maybe store it on a phone. Maybe you could access it from a Raspberry Pi. Maybe you could access it from your laptop. What if you could access Ethereum without running a full node, with almost instant sync times and being able to access the entire JSON RPC, which is how people interface with Ethereum today. Oops. But that's not all. What if you also had full archival access to Ethereum? So I know this is kind of ridiculous because if anybody has ever tried to run an archival node before with Geth, you know that instead of 1 terabyte of storage, you would need 20 terabytes of storage, which is kind of bonkers. But the idea is that, well, if we distribute all this data, and you can look it all up, something like this should be possible. So how does this network of distributed data tie back into full nodes? How do we improve full nodes? Well, there's this Ethereum improvement proposal named 4.4s. Currently, it's proposed as being deployed in 2 stages. The first stage would be Genesis to the merge, as this is more of a solved problem. And then after that is deployed, there would be, I guess, the second half, which would be the merge to around 6 months. How does this relate to Dev P2P, the current way blocks are gossiped on Ethereum? Well, advertising blocks on Ethereum would be shut off, so your only way to access historical blocks would be through other methods, such as the one we're building, or something like, I guess, bulk archival formats, which something like Arrow1 files, which is just like a file format which stores headers, transactions, and receipts in around 8,000 block chunks. How will this affect syncing? Instead of syncing from Genesis, you'll sync from checkpoints. And how will this affect archival nodes? Will I still be able to run one? And the answer is yes. Instead of syncing from dev P2P, you'll just sync from a bulk block formats like R1, as I said before. So I guess you have this, I guess it's like, why is 4 force important though? It's because instead of storing, I guess, a terabyte of storage, you can reduce that by around 750 gigabytes, so you only need to store around 250 to 300 gigabytes of storage. Chain data takes up a lot of your storage, and it's not really used for anything because everything what's useful, quote unquote, is already executed in Ethereum's global state. So currently, old block history is mostly for like researchers and people who want to sync the chain from Genesis, for now at least. So I'm going to let Nick go over on how does this crazy thing work.
All right, so now I'll go into a little more detail on how the sausage is made. Kolby explained basically the overview, and I'll go into the details. At its base, we use a distributed hash table, the same kind of protocol you'd find in BitTorrent. This is how we address our nodes and the content around the network, and how it's basically the way Portal Network, or the foundation of the Portal Network. Portal Network uses the exact same disk v5 layer that Ethereum runs on to find nodes on the network. We use the same talk-rec messages, but within these talk-rec messages, we embed overlay protocols, and these are specific to the Portal Network. And the best way to think about this is we have 3 different overlay protocols at the moment. We have history overlay, which chain headers, bodies, receipts, and then state, which is state data. And those are 2 separate overlay networks, but together they serve the data you'd expect to get from any execution layer client. And then we have the beacon network data, which provides the data that we use to sync with the head of the chain. So this is the Portal Wire protocol in a nutshell. This is the set of messages we use to find and check liveness of peers on the network. It's also how we discover new nodes around the network. Then another set of messages to directly send the content that you want between peers. And then the final set of messages is used to gossip and broadcast the content being stored around the network so that it finds its eventual home or node that's responsible for storing it. So briefly, or just like a general overview, if you think of each overlay network can be thought of as like a 256-bit key space, and each of these little circles represents a node participating with a certain overlay protocol. Now, these circles all, in theory, have different sizes. You can't really see it, but we have a big circle down here with a big radius. And so every node has an associated data radius. And this is determined by how much storage you're willing to allocate to the network. So if you're willing to allocate 100 gigs, you'll have a fairly large data radius and be storing a lot of data. If you're allocating 1 megabyte, you'll have a tiny radius and probably won't store much at all. So your node ID addresses your node around the key space, and every piece of data that we're storing inside the storage network is basically a key value pair. And to generate the content ID, we take the hash of the content key, which also evenly distributes the content around the network, so no single node is responsible for an unfair amount of storage. And then basically, like as a single node, you're responsible for storing all of the data that falls within your data radius. And then when a peer wants a specific piece of data, they calculate the content ID and they traverse the network until they find a node that's close enough to the content, and then they simply exchange the content. So what we've described so far is basically just a database, a large database, and an empty database is not very useful. So you might be wondering, where does the data come from? And the data comes from a special kind of node called a bridge node. And from the perspective of the network, bridge nodes operate like any other node. They participate in all of the wire protocol messages. The only difference is every bridge node on their back end is connected to an execution or consensus or both client, and then the bridge node is responsible for pulling data from the Ethereum client, translating it into the portal format, and then using that offer message before to broadcast the data into the network. And this is where the data comes from, and then once it's in the network, it's available, and we have different nuances to our protocol to make sure that it's always available. All right, so we have data, but like, how do we know this data is real? We do this by using the different overlay networks, and depending on the specific piece of data, there will be nuances to exactly how it is validated, but the most generic example is, let's say you start with the state network at the bottom and you fetch an account balance. The account balance will have a proof, the data you receive will have a proof attaching it to the state root. So then after you have the piece of state network data, you'll go to the history network, you'll go look up the associated header, validate the proof against the state root in the header. But now you have a header and you're not sure if that's real or not. And so then every portal client will be running the beacon network, and we use the beacon network to sync with the head of the chain. And in this way, there's various nuances and accumulators and the proofs we use and the data types that are passed around the beacon network, but this is how we validate headers are canonical, and this is how we establish a chain of validation. Trade-offs. So what's the catch? We've described something very cool here, but it's not always so easy. Like with most things in life, there are trade-offs, and in the trade-off between storage requirements and speed, we're leaning heavily into prioritizing, minimizing storage requirements. So a full node will always be faster than the portal network, but the portal network is comparable. If you're using Infura, you have network requests. So it's, for the average Ethereum use case, the latency of network requests is totally acceptable for users. If you're not sort of the power user of an Ethereum node, then the portal network, especially with its minimal resource requirements, should be more than enough for your use cases. The current status of the portal network. So we have our 4.4's history network live. It's live right now. Anyone here can spin up a node, participate in the protocol, and fetch any data from pre-merge history network. And that's cool. But we also have a testnet, which we just launched, a couple weeks ago. And on the testnet, we're running the state protocol and the beacon protocol, and we're sort of going through the final phases of testing the beacon network, and the state network is still in the earlier stages, but we have a live testnet for this, or we have live state data on the testnet as well. Throughout development, we have developed a suite of testing and monitoring tools. GLaDOS is our main public-facing network monitoring dashboard, and we'll show that in a second. And Portal Hive is our version of Ethereum Hive, and we use that for client interop. Client implementations, we have Fluffy, which is written in NIM. We have Trin, written in Rust, which is what Kolby and I are working on. We have Shisui, written in Go, and Ultralight is written in JavaScript. So if any of you guys are interested in getting your hands dirty, all of these repos have issues. You can go check it out and start contributing right now, even. All right, what's the future of the Portal network? Well, our two priorities right now are getting Beacon network pushed to production and State network pushed to production. That is sort of our MVP story that we're really targeting by DevCon, to have live state data available and validated using those three overlay networks. We also are working on a Verkle support for state data, so we'll be ready for the Verkle transition. And as always, there are plenty of optimizations to be done to reduce the existing network latency. And then after that, we're going to be working on flushing out the archive, or really just filling the state data, network with all the archive data so that we will have this global archive node that anyone can use. And eventually we want to be in everyone's wallets. We want all the wallets to use this decentralized provider to access the Ethereum protocol and to try and wean ourselves off of Infura, etc. All right, we're going to do a little live demo, and we'll see how it goes. All right, so, sorry, I don't know if you guys can read this. But basically, all I'm doing here is, in this window, I'm just going to start a trend node locally. You'll see it's right now it's getting its external-facing IP to generate the ENR. And then after that, it'll connect to the boot nodes, and you can see we're bonding with boot nodes there. Some boot nodes are, 2's not bad. Okay, so now I'm just going to run a Python script. And okay, so the content that exists in the history network is addressed by block hash. So I'm using Infura. I know I shouldn't, but I'm using Infura to just look up the block hash for a random block from Genesis to merge. And then if you see on the second half, I'm just using Web3 just like a generic Ethereum Web3 client, to connect to Trin, and then we're sending the standard ETH JSON RPC request with the block hash, and we'll try and retrieve that from the network, and hopefully we're able to retrieve it from the network. So there we got block 14 million something, and so so here's the state root from the block, uncle's root, receipts root, transactions root. Cool. So it's not the flashiest demo, but it's cool. Anyone can spin up a client, connect to the network, and you have all of this data available to you based on like this distributed data storage model we have. All right, so just a little bit more. This is GLaDOS, as I mentioned earlier. Currently, we're displaying the 4.4 stats, and 99.8 over the past, we have maybe literally a couple blocks left to fill out in this network, but the vast majority of 4.4's data is in there. In the top right, you can see the different clients that I mentioned earlier in their implementations, the ones that are active in the network. This is a graph. Oh, I'm not going to explain everything. It's cool. You can go look at it and play around with it. This is our audit dashboard. So we're auditing. This is just a long-running process that's auditing all the expected content keys and making sure that they're available on the network. I picked an audit earlier. There are more fun audits to look at, but I wasn't able to find one. But basically, you can see this is a visual representation of how a node traverses the DHT to try and find a target piece of content. We have the originating node here. It sends out requests for the piece of content to peers. 2 peers responded, not with the or 1 peer responded, not with the content, but with a list of peers closer to the content that itself. This peer responded with the same thing, and then eventually we ended up finding the content from a peer. 2 hops to find the content. We also have I'm just sort of showing things from GLaDOS. This is a network explorer, so this is a 24-hour snapshot of all the nodes that were seen on the network and their active status based on the ping pong message. And as you can see, some nodes drop off, some nodes come back online, but we also have a majority of nodes are just constantly available. And Kolby, if you want to describe the state network.
Sure. This is our, our testnet instance of GLaDOS running on our testnet called Angel Food, which is a kind of cake. Currently, we're auditing, state roots. So our state root strategy basically, starts out a state root and then does a random walk of the tree to an account. If you make it to an account, that's a successful, I guess, audit. And if you don't make it, then there is a failure. So currently what we're working on is executing all the blocks so we can, I guess, get the intermediate like state diff so that we can gossip it. Because basically in a Merkle-Patricia tree, when you delete a node and it regenerates, if it's a branch node, with only one child, it converts to an extension node. And we need to, I guess, properly track what is changed so we can gossip down the network, and then execute all the blocks, and then I guess the state network's like done?
There you go, just like that.
Yeah, just like that. So I just need to execute all those. Shouldn't be too hard.
Cool, so thanks for listening. We've been working on this project for a while, and we're really excited that it's live and available. Please run a client if you're so inclined, especially if you have validator somewhere running. It's very trivial resource requirements to spin up a node alongside, and you're really helping the network. We have our specs on GitHub, but really the best place to start is our website, ethportal.net. We also have the GLaDOS website. You can find everything from the website, ethportal.net. The best place to contact us to get help or just ask questions about how it's working, what's going on, would be our Discord server, which you can also find on our website. So, cool, thanks a lot.
Right, are there any questions? Thank you. Yeah, okay. Thank you very much. Awesome, this network. You mentioned the the data radius, I think. So each and every node in a network has a maybe different radius, and you mentioned, I think, 100 megabytes. So this is all the client has in the end, or how much data does it have?
It's up to the client to define how much storage it wants to contribute towards the network. So if a client only has 100 megabytes available, the data radius is dynamically set based upon the config, basically.
Ah, okay.
And that broadcasts to the peers on the network what data you can expect to find from that client.
Yeah, okay, makes sense. And the end vision then is that we have this portal network, and then you mentioned, of course, in the beginning that there are light clients probably running on smartphones, and these actually have not that much storage, so just, are they also contributing then to the portal network or just accessing it?
You don't have to contribute storage to the portal network to access the data, but our expectation is that defaults are more than sufficient. Of course, people could spin up many clients with zero storage, but the lazy thing is most people will just run the client with the defaults, and we also expect that there will be, we expect that there will be plenty of storage because cumulatively it's not a wild amount of storage required for each network.
Okay, thanks. Any other questions?
Hey, thanks for the talk. I'm curious, could the clients be used for transaction tracing as well, given that they have access to everything? They would probably need to run the VM and stuff, but yeah, is that an option? Have you thought about that?
I believe it's possible. It might take a fair amount of network requests, but yeah. All the data is available on the network, so.
This question is not going to be very smart, but is it possible to build a wallet that uses the portal network instead of an RPC provider?
That's a very smart question. Yeah, of course. That's
the goal.
Maybe I didn't stress it hard enough, but that is the dream. Yeah.
So if it's a dream, what's the main blocker there, or what do you have to figure out in order for it to be reality?
I guess I'll take this. So I guess the first thing is being able to execute all the blocks, which is what I'm currently trying to do. Once we have a network with all the archival history, well, that is looking all that up is pretty slow because you would have to walk the tree on the network. So after that is, we're looking to, I guess, upgrade our history, our state network with, I guess, faster lookups, and we'll call this like, I guess, head state. So instead of doing like log n lookups, so instead of having to walk the tree to find your account on like the latest, like, I guess, instance of the state, you could do a lookup directly on the account you're interested in.
Just another follow-up question. So RPC nodes are used for querying data, but they're also used for compute. So would the portal network do anything for the compute side of things, like when you interact with a smart contract or anything, there's some compute that needs to be done? Is it also part of the scope, or?
I guess the way to answer that is maybe you're referring to something like an ETH call? Yeah. So you could do an ETH call, and you would just like run an instance of the Ethereum virtual machine on your local machine, and then you could just like, I guess, walk the tree, or if you're doing head state, hopefully we have like, I guess, O of 1 lookups at that point, and yeah.
All right, thanks so much, guys.